Hi, I am Arup Biswas, a PhD student in physics. I broadly work on the areas of fast passage processes. So today I shall introduce to you what is a fast passage process and how we can relate it to the classical random walk. So before jumping into what is the main focus of my talk, I would first wish to pose a problem in front of you. The problem is like that. There is a gambler who wishes to win the jackpot amount. What it needs to do, it will play a game. The game is like that. It will toss a coin. If the coin gives head, it will move one step to the right, and if the coin gives tail, it will move one step to the left. And by doing so, whenever the gambler reaches +1 for the first time, it will win the jackpot amount. So the game is very simple, but the thing is, each coin toss will cost him $1. So you can just start thinking about what approximate time that the gambler may need to reach +1 starting from 0 by playing this game. So I shall come back to the answer at the end, but before that, let me introduce you to the classical random walk. Some of you may know that. So there is a person sitting at 0 and it tosses a coin. If the coin toss gives head, it moves to the right, and if the coin toss gives tail, it moves to the left. Now, and again, after moving to the left or right, it again follows the same rules, that it again tosses a coin and moves accordingly. And also we assume that the coin is not necessarily be a unbiased coin, that it can give head with some higher or maybe lower probability with probability small p, and it can give a tail with probability small q. Now we ask that after playing this rule, what will be the final position of the walker after some smaller number of steps? So for sure it will be a random quantity, it will be placed randomly after smaller steps, but let's just count it. For n is equal to 1, it has taken only one step, so only one step can be it can get either head or tail only. When it gets head, it moves to the right, so its final position is +1, and when it gets tail, it moves to the left, so its final position is -1. For the case of n is equal to 2, there are 4 possibilities. It can get one head and one tail, so it moves one step to the right and one step to the left, so its final position will be again 0. For it is another possibility that it can get 2 consecutive heads, then it will move consecutively 2 steps toward the right, and its final position will be +2. It can also get one tail and one head, again its position will be again 0, and it can get 2 consecutive tails also, and in that case also it will move 2 steps towards the left, and its final position will be -2. For n is equal to 3, you can again do these boring calculations and see that there are total 8 number of possibilities that the walker can move, and its final position will range from -3 to +3. So rather than doing these brute calculations, can we say something in general for n number of steps? So what we ask, what will be the position of the walker after n number of steps, which is given by x. So this is the only technical slide that I have in my talk. So if you can't follow, please you can skip it. It's not that I will use in the latter part of my talk. So the thing is, after any n general number of coin toss, it has 2 to the power n possibilities to move. Why? Because each coin toss have 2 possibilities, head and tail. But so if you toss it n number of times, you have 2 to the power n possibilities. Out of that, let's assume we got n1 number of heads. So how many ways you can get n1 number of heads? It's given by simple combinatorics by this number. And then if you can easily calculate the probability of getting n1 heads out of n coin toss, which is given by this number divided by the total number of possibilities that you can have in your experiment, which is 2 to the power n. And the final position of the walker will be decided how many steps it has taken to the right minus how many steps it has taken to the left. That is number of heads minus number of tails. You can do this simple calculation and find the probability of the walker to being at any position looks like this, which looks like a bell curve, which is exactly Gaussian if you know, and you see the curve is peaked around 0. That means most of the times if you repeat the experiment, you will find the walker only around the 0 position. But you can also see that when I increase the number of steps from 200 to 400 to 600, the curve starts to spread out. That means not only mean is the all thing about this system, you also need to know how much it deviates around the mean position, which is, and the deviation or the error given by this dashed line, which measures how much its spread of the curve. And you can clearly see the spread increases as you increase the number of steps, and it increases linearly with respect to n. So that's the basics of random walk. Now I come to my main thing that I work on, not exactly on random walk, but the first passage. So what is first passage? I say when the walker reaches +1 for the first time, it stops its motion. So I will repeat again. While doing the random walk, whenever the walker reaches +1, starting from 0 for the first time, the motion is complete, and you say the first passage has occurred to +1. So you can again ask, what is the probability that it will reach +1 starting from 0 after n number of steps? For n is equal to 1, it has that means that it has to reach +1 just at the very first step. That means at the very first step, it has to get ahead. There is no other way. So it gets ahead at the very first step and reaches +1, and the corresponding probability of getting ahead is p. So phi1 is p. For n is equal to 3, the only way it can reach +1 after 3 steps is this combination, 1 tail, 1 and 2 heads. And the corresponding probability is p square q. Why p square? Because there is 2 heads, and why q? Because there is 1 tail. Analogously, for n is equal to 5 also, you can find the corresponding probability is given by this quantity. There is p cube because there is 2 heads, there are 3 heads, and q square because there is 2 tails. And the p factor 2 comes because now it has 2 possible ways to reach +1 starting from 0. And you can do this calculation for any general 2n-1 number of steps and find this complicated expression. But don't bother. To get a feeling for what this expression actually means, we ask a very simple question. That is, starting from 0, we ask what is the average number or approximate number of steps that it will take for the walker to move to +1. Just an average quantity, average steps to move to +1. And this can be simply found by this quantity. So this is the result. So you see the mean number of steps to reach +1 from 0 is given by 1 by p minus q. And when p is equal to q, that is, the coin is an unbiased coin, it gives head and tail with equal probability, you see the mean number of steps diverges. So even the walker starts at x is equal to 0, the steps it needs to +1 on an average is infinite. So which is a bit counterintuitive, but at the same time you see the probability that, like, if you sum for all the probabilities phi n, it is constant, it gives exactly 1. That means, in conclusion, starting from 0, the walker will reach +1 for sure, with guaranteed, but it will take an infinite number of steps to reach there. So I shall come back to the question I asked regarding the gamblers, that how many times the gambler needs to play this game to get the jackpot amount. So you may already infer from the last example that the gambler has to continue playing an infinite number of times so that it reaches the jackpot amount. And playing an infinite number of times means it has to expend infinite number of cost or money to win the game. So the answer is the gambler will win the jackpot for sure, but it has to expend an infinite number of money to win the game. Thank you.
Thanks a lot for this lovely talk. So we'll have to take you whenever we actually go to Las Vegas or something. Okay, so any questions from the audience?
I'm just curious, given you're in the physics group, is there a physics application to this?
A random walk applications?
No, the gambler's ruin application.
Gambler's ruin application, then, okay, let me think. No, I have not seen, there has to be an application, but this is only the thing, intuitively I think, so I don't know.
How did you come upon this? I mean,
so this is the first thing that I just encountered while reading about fast passage processes, and that seemed a lot of counterintuitive to me to appreciate this result. So yeah, there is application for sure, but I don't know in real life how people actually use this formula to this. Thanks.
Also, there is one more question.
Can we somehow use the intuition that the process is memoryless? Like you said, when suppose the probability of heads and tails are both half. So once it reaches from 0 to -1, now reaching +1 has become harder because we can think of it as starting from -1.
Right,
and reaching
absolutely, right.
2 steps forward. So can that be used to get more insight on
So, okay, so you want to introduce memory that if it goes to -1 and fails, that it remembers that I have come to the wrong direction and I won't go there again?
No, like that can give us more intuition that in expectation we will need infinite amount of time.
Yeah, so what is the question? I did not get.
Like once we get a tails, we go to the left side.
Right, yeah.
Now reaching +1 has become harder.
Absolutely, yeah. So I did not actually tell why it happens so. It exactly because of what you told right now. So when it goes to -1, it seems like it has started a motion starting from -1 itself. So because it does not remember from where it started when it goes to -1. And again, it has only one way to go to the right, but it has infinite number of ways to go to the left. So that actually gives rise to this infinity time. Okay, thanks.
Okay, so we'll thank the speaker again.